Question 5, part B, part I. We need to find the center of mass of the swing boat. It's made of two rods, OA and OB, and a circular seat AB. We know the position of the center of mass of each rod because they are uniform rods. So the center of mass of each rod is distance 3a from O. Obviously, the position of the circular arc is clearly the center of mass of the circular arc lies on the vertical line going from O due to symmetry of the boat, and we need to find it. Yeah, where is it? We can use the formula book in order to find the position of the center of mass of the seat, because it's a circular arc, and we have the expression for the center of mass of the circular arc radius r angle at center to alpha. Then the distance from the center for the center of mass will be given by r sine alpha over alpha. Now we can substitute the values we've got in our case. R is 6a. Now the angle for the arc, the angle subtended by the arc, is 90 degrees. We have to use half of this angle in our formula, which is pi over 4. So we've got sine pi over 4 over pi over 4, which gives us 24a root 2 over 2 over pi, or after simplifying the expression at the top, we've got 12a root 2 over pi. So that's the distance of the center of mass of the seat, the circular seat, 12a root 2 over pi. Now we can consider three particles, mass m, and 3m, placed at these 3 points, and we can find the position of the center of mass for this system of particles. Let's make a table. What do we have? We have rod OA, we have rod OB, we have the seat AB, and we have the total swing boat. Mass and the position of the center of mass. Why? I only consider the vertical position of the center of mass of the board, because obviously it is symmetrical about the vertical line, and the center of mass of the system G will lie on this vertical line. We'll measure all the distances from O downwards. For rod OA, mass is m, and its vertical distance from O is given by 3a cos pi over 4, which is 3a root 2 over 2. We've got the same expression for rod OB, 3a cos pi over 4, 3a root 2 over 2. Seat AB mass is 3m, and it's 12a root 2 over pi. So the total mass for the swing boat is 5m, and we are interested in the position of the center of mass. Let's write down the equation. So what we know that 5m y is equal to the product m times 3a root 2 over 2 will appear twice in our sum, so we can write down 2m 3a root 2 over 2 and plus the product of 3m and 12a root 2 over pi. So m is cancelled and the value of y is given by 3a root 2 1 plus 12 over pi all divided by 5 will give us 4.09a as required. And that's the answer to part BII. Let's have a look at part BIII. We need to find the maximum angular speed of the boat when it is released from the position when OB is horizontal. Let's draw a diagram. We need to see where the initial position of the center of mass of the boat is. We know that it is distance 4.09a from O, and if OB is horizontal, the angle between OG and OA is pi over 4. And that's the angle between OG and the vertical line down. The maximum angular velocity of the boat is achieved at the lowest point. So when G is vertically below O, this position. So if we label it as G dash, say. So that's the situation here with the center of mass. Now, we can use conservation of energy in order to find the maximum angular velocity at this point. Let's assume that at this moment we have zero gravitational potential energy. So at this level, GP is 0, and we'll measure GP with reference to this point. So what do you have initially for the energy? It's gravitational potential energy plus kinetic energy, the total mechanical energy. So GP is given by mgh plus kinetic energy is 0 because it's released from rest. Now, mass, the total mass of the swing boat is 5m multiplied by g. Now, in order to work out the distance h above the 0 GP level, we write down the expression 4.09a. Yeah, so that's distance here, 4.09. Take away 4.09a cos pi over 4. which will give you 5mg 4.09a 1 minus root 2 over 2. And that's the initial mechanical energy of the system. Now, what do we have finally at the lowest point? Again, the total mechanical energy is Gp plus kinetic energy, but Gp is 0 at this point, and kinetic energy is given by half I theta dot squared. So we've got 1/2. The moment of inertia of the swing boat is 132 ma squared multiplied by theta dot squared. Energy is conserved. Energy is conserved because we assume that there is no friction, no air resistance. So we can write down the equation that 5mg 4.09a 1 minus root 2 over 2 equals 132 divided by 2 is 66 ma squared theta dot squared. Now, if a equals 0.5, we can work out the numerical value of theta dot squared. Yeah, but before we can cancel, 1a here, we can cancel m. So after all calculations done, we've got the value for theta dot squared as 1.779, which gives us the value of theta dot as 1.33 radians per second. Three significant figures.